Hello students, welcome back to my channel. Today we will study the topics of group theory which would be useful in TIFR exam. That is, we will study some questions related to Sylow theory and some of its results. Now let's get started. Now let's discuss some questions. If order of G is equal to 12, that is 2 raised to power 2 into 3, then Sylow 2 subgroups are of order 4 and Sylow 3 subgroups are of order 3. One number of them would be 1 plus 2k divides 12. Basically, 1 plus 2k divides 3 because it cannot divide 4. Similarly, 1 plus 3l divides 4. Therefore, k के पास हमारे पास कितनी choices है 0, 1 and l के पास कितनी choices हैं 0 and 1. Another question. Order of G equal to 36, which is 2 raised to power 2 into 3 raised to power 2. For that, Sylow 2 subgroups के आपस कितनी choices रहेंगी 1 plus 2k divides 9 and 1 plus 3l divides 4, that is l is equal to 0 or 1. Here k is equal to 0. 1 is also true. For 2 it is 5. 5 does not divide 9 and 4. Now, for order of G equal to 2 into 3 into 7, we have Sylow 2 subgroup 1 plus 2k divides 3 into 7, that is k is of the form 0 or 1. For 2 it is 5, 3, 7, 4, 5, then it would come 10. For Sylow 3, we have 1 plus 2k2, 3k2 divides 2 into 7, which in turn implies k2 has choices 0 and 2. For Sylow 7 subgroup 1 plus 7 k3 divides 2 into 3, which we have only one choice, that is k3 is equal to 0. Therefore, unique Sylow 7 subgroup, which in turn implies G is not simple. Hence, we also have a property that if order of G is PQR, where PQR are distinct primes, such that then there exists unique Sylow R subgroup. Now another question. For G to be a simple group, an order of G is 168. Find the number of Sylow 7 subgroups of G, which is 1 plus 7k divides order of G, that is 1 plus 7k divides 168 की factorization पे आएगी 7 into 2 cube into 3, 2 cube into 3, which has only two choices for k is equal to 0 and 1. K cannot be equal to 0 since it is a simple subgroup which is given, and hence k is equal to 1. That is 8 Sylow 7 subgroups of G. To prove using Sylow theory that if order of a group G is PQ, where P and Q are distinct primes such that P doesn't divide Q minus 1, then G is cyclic. Its proof, we will count number of Sylow P subgroups, that is NP equal to 1 plus KP divides Q. In that case, 1 by Kp is either equal to 1 or Q, because since Q is prime, it has only two divisors, 1 and Q. But as we know, P doesn't divide Q minus 1. Therefore, 1 plus Kp cannot be equal to Q, which in turn implies Np is equal to 1. We have a unique Sylow P subgroup, and hence it is, if we say H to be the Sylow P subgroup, then H is normal in G. Now let's count number of Sylow Q subgroups of G. In this case, 1 plus K dash Q divides P, which in turn implies NQ is either equal to 1 or P. If NQ is equal to P, it implies that Q divides P minus 1, that is, Q is less than or equal to P minus 1, which is a contradiction, because obviously if there are two distinct primes, one would be greater than the other. So we have assumed here that P is less than Q. Hence, in this case also, we arrive that we have a unique Sylow Q subgroup of G, which we take to be K, and therefore K is normal in G. Now, we have that order of H is P and order of K is Q, and H intersection K just has identity, because H intersection K का जो order होता है, that should divide order of H as well as order of K. And since order of H and K वहाँ पास distinct primes है, therefore order of H union K divides 1, and hence it is identity. And H or K normal subgroups of G है, so it implies that its elements commutes, that is HK is equal to KH for all H belonging to capital H and K belonging to capital K. Now, since these groups are of prime order and prime order groups are cyclic, therefore we assume that H is generated by A and K is generated by B, such that order of A is P and order of B is Q. We also have by this condition that AB is equal to BA, which in turn implies order of A and order of B का जो GCD है, that is P and Q is 1. And hence we have that order of AB is equal to order of A into order of B, which in turn implies PQ, which is equal to order of G. Hence we have got one element in group G whose order is equal to the group of G, which implies G is cyclic. For order of G equal to P square Q, where P is less than Q, such that P doesn't divide Q minus 1 and Q doesn't divide P square minus 1, implies G is abelian. Another which we have is order of G equal to P square Q square, such that Q doesn't divide P square minus 1 and P doesn't divide Q square minus 1, implies G is abelian. Another result which we have is P the Sylow P subgroup of finite group G, then P contains all the elements in normalizer of P, which is of order P raised to power some power of P. Normalizer of P is contained in P. Now counting of subgroups. For order of G equal to PQ with P less than Q, G non-abelian. For G to be abelian, P doesn't divide Q minus 1, P divides Q minus 1. We have for G non-abelian and P doesn't divide Q minus 1, it cannot be possible because for P in the case when P doesn't divide Q minus 1, we have that G is cyclic and hence abelian. Therefore, if G is cyclic, G has unique subgroup of order 1, P, Q and PQ. Now, in this case, for G non-abelian and P divides Q minus 1, number of subgroups of order P is Q and rest we have unique subgroups of order 1, Q and PQ. In the there is no case like this, and in this case, number of elements of order P are Q into phi of P, and number of elements of order Q. Why we have taken because there are Q subgroups, Sylow P subgroups in G, and Sylow P subgroups in G, these are distinct, and hence we have multiplied Q. And here it was unique subgroup of order Q, therefore only number of elements of order Q is phi of Q.